Well, now that we know that pressure is something that we need to take a look at when we're monitoring a gas, you might be wondering, how do we actually measure pressure? And there's two different things that we can actually measure. We can measure the pressure of the atmosphere, or we can measure the pressure of a trapped sample of gas. And unfortunately, when you're measuring the sample of a trapped sample of gas, we often also need to know the pressure of the atmosphere. So we're going to have to kind of do both at the same time. So let's focus in on one thing at first, and that would be, how do I measure the pressure of the gas in the atmosphere itself? So Earth is surrounded by this tremendous blanket of gas, and gravity is constantly pulling that blanket down toward the surface. So if you could investigate just a column of air from the surface of the planet all the way up to the upper reaches of the atmosphere, you'll kind of see something that might look a little bit like this. Toward the upper end of the atmosphere, you're not going to see very many gas particles because it's further away from the planet. Gravity isn't pulling it down quite as hard. Whereas closer to the planet, gravity has more of an effect and it's pulling those particles closer and closer together. Also, those gas particles are kind of pushing on one another, pushing them back down toward the surface of the planet. So they're nice and smushed up next to each other, all down close to the planet's surface, whereas way up in the upper atmosphere, the gas particles are not going to collide next to each other very much. And this has everything to do with gravity and gravity's effect on these little gas particles. So just so that we're kind of aware, up in the upper atmosphere, if I was going to measure the pressure, you'll notice that there aren't very many gas particles that could collide with any sort of container. That pressure in the upper atmosphere would be considered to be very, very low. Whereas way down towards sea level, you can notice that there's a ton more particles per square inch, or however you'd like to measure that, per area. And that would result in a very, very high pressure. The tool that we typically use to measure atmospheric pressure is called the barometer. And the barometer is constructed quite simply from a giant pool of mercury and a tall glass tube with mercury in the inside that has been inverted so that it creates a vacuum at the top. And all you would have to do is to measure the column of the mercury on the inside of this tube to kind of relate it to pressure. You'll notice those two little blue arrows pushing down. The atmosphere, the gas around this pool of mercury, is constantly pushing down on top of this little pile of liquid. And if the pressure is high, the liquid would like to escape that pressure. So it actually starts squeezing itself into the tube and up the tube toward the vacuum. If the pressure of the atmosphere isn't so low, well, then the mercury can come out of the tube and kind of go back out into the pool. So how do we use this weird device to actually calculate the atmospheric pressure? Believe it or not, there's actually a pretty quick and simple little formula. So if I would like to know the pressure of the atmosphere, I would need to take into consideration a couple of things. First of all, the height of the liquid on the inside of the column. Next, the actual identity of the liquid. The density of the liquid here really, really matters. The more dense the material, the less high it can actually climb inside of the column. The more dense the material, it wants to stay quite low. The less dense the material, it can actually go quite high. So density here matters. And then finally, the force of the gravity pulling that liquid back down into the chamber. So you'll notice over on the side, we actually have a formula that's started to kind of populate. Pressure equals HdG, height times density times gravity. And I'd love you to see how this actually works, but you're going to need to know what units you need to plug into this, because we have a ton for height, we have a ton for density, and gravity can also be kind of complex as well. So let's limit our unit scope here. As far as height is concerned, please always make sure that the unit is in meters. Density is kind of in a weird unit for this calculation. Kilograms per meter cubed. Typically you're provided with grams per centimeter cubed, so you would need to convert your densities before you actually use this equation. And then finally, G, the force of gravity, is a constant, 9.8 meters per second squared, and that can just be a plug and chug number that goes into there. Pressure, therefore, will always have the same unit after this calculation is done. Pressure will come out in the unit of pascals. Let's see this calculation in full force. So here's an example problem. What is the pressure recorded with a barometer filled with mercury that has a density of 13,560 kilograms per meter cubed? The height of the mercury inside the barometer was recorded as 742 millimeters. Well, let's start populating our equation. First thing I notice is that I've been given a height, but I need that in the unit of meters. Right now I have 742 millimeters. That would equate to 0.742 meters. Next up would be density, 13,560 kilograms per meter cubed. I can actually directly plug and chug that into my unit here. Unfortunately, again, it's not always given to you in kilograms per meter cubed. That might be something that you need to convert prior to putting it into the problem. And lastly, my plug and chug number, G, for gravity, 9.8 meters per second squared. You're now ready to go to the calculator and kind of plug and chug out your answer. And that ends up being 98,600 pascals. The real big take-home message here is you absolutely need to make sure that you convert all of your units before you plug and chug this into this very simple P equals HDG formula.